Hello, my people. Wish I could be with you, but I'm going to try to do this lesson through a video again. So have this sheet of notes out. We started it just yesterday, and we're going to keep going with it. And I promise I will play you the song tomorrow when I'm back in class. But you should remember that we were building a function, and our function was the doubling function, where 2x is, or what are we doing? Okay, we're taking 2 as a base, raising it to the x power and letting x change, letting x grow, and that doubles all of our y values, and it creates this la 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 la. I can't do it on a video. It creates our graph of this exponential function. And then we talked about how we have this asymptote, a horizontal asymptote here on the left end, and the right end just kind of skyrockets up. The domain of the function was anything for x, but our range output values, we were never going to get anything negative. It was always going to be positive values, big positive values on the right end, and very small positive values diminishing to 0 on the left end. So let's go from there. Our next function is what is called the halving function. It's got a base of 1/2. And what's that going to do? Let's do the building of it the same way we did up above. So let's start with x equals 0. Now remember, 1/2 is raised to the 0 power, and like anything, any other base to the 0 power is 1. And then using x equals 1 as an exponent, 1/2 to the first power is 1/2. Using the 2 now, we've got 1/2 squared, so 1/2 times 1/2, that's going to be 1/4. And remember, this is called the halving function. So as we take one step forward, one unit forward, we should see a 1/2 of the previous value. So cutting each value in half with each step forward we take. So half of 1/2 is 1/4, half of 1/4 is 1/8, and half of 1/8 is 1/16, and so on and so on. So as x continues to increase indefinitely, where are our y values headed? Our outputs are headed towards smaller and smaller numbers, headed to 0 here on the right end. And as we work backwards with a -1, let me again remind you, we're going to put -1 into that exponent. So 1/2 is going to be raised to the -1. And remember, a negative exponent means we reciprocal the base to change it to a positive exponent. So this is the same thing as 2 with a positive exponent of 1. In other words, this equals 2. Okay, and that should make sense, because if I'm going to get half each time as I go forward to the right, then I should be reversing that. Going towards the left should be doubling my values. And 1/2 doubled is 1, and 1 doubled is 2, and so on. So you should be able to fill this out. 2 doubled is 4, 4 doubled is 8, and so on. And so as we move further to the left, letting x grow more and more negative in value, our y values are just doubling as we walk that way. And so this is headed to, I hope you know, infinity, growing forever. Okay, so let's draw that as a graph. This time we have really super high values on the left end. We hit 1 from high values, hitting 1 and then diminishing. So I'm going to let the horizontal asymptote now be on the right end at 0, and we're going to see this fall. No, I do not have a song for this. I don't know how to play the record backwards. So that's what we call decay. And in fact, let's talk about that. So why did this graph decay while the other graph, our first graph, our doubling function, while that one was exponential growth? And the answer to that lies in the value of b. So in this case, b is the base 2. b is greater than 1. We talked about that on some earlier notes. b is greater than 1 creates growth, and decay, what was our value of b here? It was 1/2. So when b is between 1 and 0, we're going to see decay happening. And the value of b cannot be negative. So those are our only two options. Now, what else do we notice about this graph? Let's talk about the ends. It's the right end where we find our horizontal asymptote. And that's the equation y equals 0. The domain is any x value we're allowed to plug in, and all of them worked. They all gave an output, and any x value would give an output. So you're allowed to plug anything into a function for exponential decay, but you're never going to get anything that's negative. All of your output values, in other words, all of your range is going to be positive, and just like up above, not equal to 0. Soft parenthesis that. All right, so you're going to have to graph these. It's time to start looking at what happens to different kinds of values for your base as well as for your value of A. So I want to talk about that a little bit here. And there's a couple of diagrams here kind of showing you what happens when you change some of the numbers, they're called parameters, A and B in your functions. And I'm going to move now to a Desmos and show you a little bit of a dynamic demonstration here. If I can figure out how to do this. Let me jump you to here. Okay, so we're looking at, right now, we're looking at our exponential growth function. And this is, if you want to write it down, I don't know if you do, this is the doubling function. This is the one we just graphed on top of your note page. So I have B, if you look here on the left side, you'll see I've got B set equal to 2. I have A set equal to 1. And I'm going to talk about K in just a minute. But for right now, this is just the equation y equals 2 raised to the x power. And you can see our doubling function. Okay, now in order to match the graph that you're looking at, I want this to say the same thing it is on your notes. You see where it says 1.2 to the x power, and it has that repeatedly several times. Each time they're changing the value of A. So I'm going to set my value of B to 1.2. Things are changing. There it is at 1.2. And I'm going to set my A value to, I'm going to leave that at 1. So this is the graph that you have on your function. You might want to highlight it if you can see it. It's the 1.2 to the x power graph, where A is 1. Now let's see what happens when A is equal to 2. And you can watch the screen here. If I let A increase to 2, make note of what happened to the graph. Now when it's at 3, we see an even different graph, and so on. I can keep changing A. So I'm going to let this kind of run so you can watch it happen. Okay, weird stuff just happened there. And then it's kind of going back to normal. That's the exponential growth graph we've decided before. What's going on down there? That is weird. Okay, let me pause this and let me talk you through it. So this is, actually, hold on, let me stop this. Okay, so that graph you saw, that was this graph right here. Is the just where A equals 1. You might make a note that A is 1 right there. And notice where it passes through the y-axis, right at 1. Now we take a look at the graph where A is equal to 2, and you should notice as you trace it that it passes right through the y-axis at the value of 2. And you hopefully notice that this is kind of a pattern we're seeing on all of them, that our A value is also our y-intercept value. That's something to probably write down at the bottom there, that the A value is the y-intercept. A is also the stretch factor. It just always has been. Each of these functions can be considered a stretch vertically of the other functions. So you might also put that, but you're probably going to see this more as the y-intercept than the stretch factor. It just happens to be both in this kind of function. Okay, so A is gonna affect the graph that way. Now let's look at what B does. So these graphs, you see we have a different base value. In all of these, they've got A set equal to 1, but the value of B is changing values, 1.5 and 2, those ones. So I'm going to go over to that demo again, and I want to show you this graph, how what happens when we change the value of B. So let's open that back up again. Now I've got A set at 1, but I'm going to change B so that it's, let me do that first one. You see the 1.5? That's the value of B I want to set this to. Okay, so there's the value of B, 1.5. Now let me increase it to 2, and you watch what happens to the graph. As I increase it to 2, now it's at 2 there. What is something you notice about that? Let me do it now up to the 3 that's on your paper. Okay, there it is at 3. And talk to your people right now. Why don't you pause the video if you need to and just have a quick conversation. What does the B value do to the shape of the graph? All right, hopefully you had a chance to talk about that. Now let's go to, I'm gonna let this run and it's just gonna let B change to all kinds of different values, and you watch the shape of the graph as that happens. Ooh, there's some funky stuff there too. Oh, here it comes back. Okay, this is just going back and forth. I don't know where it went there. Okay, I do know where it went. And we're done. Okay, so let's do that a little bit slower. Okay, so notice the value of B, 2, 2.4, 2.9, and so on. It's getting bigger and bigger. As I let the value of B get smaller, let me have it decrease down from 4. Here it is at 1.2 again. Here it was at 1. Look at that. Look at that graph when B is 1. Y equals 1 to the x power. I think that should make some sense to you. I hope so. Now we let B go less than 1. And how does this change our graph? What happens when B is less than 1? You end up with decay. I hope you see that. So if B is less than 1, we get decay. And if B is 0, our graph disappears. And all these negative, here's B is negative 0.8, 0.9. We don't have a graph at all. This is again because the base has to be a positive number. And it can't be 0, or you get that. And it can't be 1, or you get that, straight lines. Okay, but between 0 and 1 is decay. Greater than 1 is growth. Okay, so some things you should notice about B is that B kind of decides the steepness of the curve. And we had big numbers like 3. That's a huge number, I know, but compared to 2. And we got a much steeper curve when we used a base of 3, which makes some sense to me because if I use a base of 3, that would be known as a tripling function. So compare that to a base of 2, a doubling function. Would you rather double your money every year, or would you rather triple your money every year? And that would mean tripling it should grow faster. In fact, look at the value when x is 1. And let's look at it on our 3 to the x power graph. When x is 1, you see how it hits this point right here at 3? And compare that to when we look at the 2 to the x graph. When x is 1, that graph hits at 2. That point is on there. So there's this extra height that's obtained. Okay, now that is a steepness factor. And when B is greater than 1, you're getting the growth. I know we've written this before. And when B is less than 1, but greater than 0, you're getting the decay. So let's look at the decay graphs. The biggest exponent, or it's not an exponent, the biggest base in each of these with these fractions, 1/3, 1/2, 0.9, the biggest one is actually the 0.9. 0.9 is larger than a half and larger than a third. And this is the least steep graph. So we almost have a reversal. With a bigger base here, we get a graph that's even less steep. So I like to think of it this way. Let's go back to the demo. And look again at when the base B is 1 and how horizontally straight that is. Now, if I let the B go a little bit less than 1, we have a curve that's kind of straight. It's not bent very much. And then I go even further away from 1, and it gets a little bit more bend to it. Even further away is more bent. So let's come back to 1 again, where it's a horizontal line. And let me go increase from 1 a little positive. So here's a base 1.1, and it's not very far away from 1. But look how straight it looks. That's actually a curve. It just looks kind of like straight. And as I let B increase even bigger, it gets more and more curvy. More and more curvy. So I like to think of it this way. The closer the value of B is to 1, the straighter the curve looks. The farther away b is from 1, the more curved or more bent it looks. See how that bends as I increase my value of b? But as I go closer to the value of 1, let me get it. There it is. Closer to the value of 1, it's very straight. And then I move further from 1 on a decay type of graph. And the further I move from 1, the quicker or the curvier it is. Okay, so let me jot that down with you. Closer to 1, let's say b. b closer to 1 means a straighter graph. b further from 1, that means a curvier. Is curvier a word? I think it is. A curvier graph. So I feel like I'm talking to a computer screen because I am, and I'm not sure if you're getting this or not, but I'm going to give you a chance to test yourself. So let's have you turn to the back of your handout. And there's some questions to try out. This is a matching set of questions. You got 5 functions, actually 6 functions listed here, and 6 graphs here. So I want you to pause the video and everybody talk together and see if you can take 3 minutes and match the graphs to the equations. And then come back to me and we'll check your answers. Pause it now. And we're back. All right, so let's see if you got these right. So I'm going to start with my 2 functions that were decay. And I know they're decay because their base b is less than 1. 1/2 and 1/3. That's going to be these 2. Now 1/3 is closer, no. 1/2. 1/2 is closer to 1 than 1/3 is. So this one should be straighter, and this one should be curvier, steeper, more bent. So we've got 2 choices. We've got graph A coming down like this, and then we have graph B coming down like this. Those are my 2 decay graph choices. So which one is more bent than the others? And I would say that's graph B. So I'm going to say that graph B is this one, the m of x function, and graph A is the k of x function. Did you match me? All right, now let's go look at these graphs that are growth graphs. And let's just take a look at our bases. And actually, I think we got to look at a little bit more. One of those graphs has an a value that is not 1. A is 3 in this graph, and all the others had a value of a that was 1. So do I have one graph that has a y-intercept that's not crossing right here at 1? Because it'll be a dead giveaway, and it's this one right here. So this graph, the C graph, should be G. That leaves me 3 more functions, and let's look at their bases. So we've got 2, we've got 3, and we've got the number e. Let me remind you that e is approximately the decimal 2.7182, ... It keeps going. And so of those 3 numbers, 2, 3, and this decimal, I'm just going to ask myself, which one of those is farther away from 1? So I'm looking for the curviest graph. Which one of these is bent the most? And I say D is bent the most. And since D is bent the most, then it must have the biggest base. So I'm saying 3 is the D graph. Now E is bent almost just exactly like that. The graph E here is pretty close to the graph D. And that's because its base is pretty close to 3. So I think that this is appropriately named, that they named that one E because its base is 2.7, which is close to 3, close to the D graph. So that leaves the F graph to be choice 1, or F of X. Also a good name. All right, now I am going to stop this video and I am going to have you guys open a new video up for the rest of this lesson because this one's getting pretty long. So I will see you in the next episode.